Okay, hello everyone. This is the fourth lecture in the Descartes online um, lecture series. And so we'll be talking about some different techniques that we use in combinatorics to essentially do counting. So specifically, there are four techniques that we'll be looking at, which are casework, constructive counting, complementary counting, and pi, which is the principle of inclusion and exclusion, or exclusion. So let's go over some definitions. Okay, so there are three definitions that we need to grasp. But before them, let's actually go over some perhaps even more basic principles that are essentially fundamental to combinatorics. So first one that we're going to talk about is the addition principle. So I'm just going to say AP. And this is essentially, well, rather than defining it with words, let's actually look at how we might think of it. It's pretty commonsensical. So if we have, for example, three types of apples, actually that's a bad picture. Actually, no, that's fine. So let's say we have three types of apples, and we have two types of oranges. Now we want to find out how many types of fruits there are. So the thing is, well, we're going to pretend that apples and oranges are the only types of fruits. And there are three types of apples and two types of oranges. So the total number of fruits or types of fruits is just going to be 3 plus 2, which is 5. So that's the idea of the addition principle. We can just add these different amount of types and get the total number of types for a larger set that includes all of those sets. So essentially, to put this in words, not really rigorously, we might say that the number of ways for a certain problem or a certain event to happen, or I'll just say problem, or I'll also number of ways for a certain problem is the sum of all the number of ways for the subproblems. So that's the addition principle. Okay, so what about the multiplication principle? This is another principle. And essentially, again, rather than starting with a definition, let's go over the idea. And everyone already might know what the multiplication principle is, because when you're learning multiplication in school, you essentially learn it sometimes by learning the multiplication principle. And it goes like this. So let's say we have, we're at a restaurant maybe, and we have three types of appetizers. And for each of those three types of appetizers, we have two types of meals. And for each of those, we have 5 types of dessert. I probably spelled it wrong, to be honest. I think it has 2 S's. Okay, so how many ways in total are there for us to order at this restaurant? Well, the idea is that for each of these 3 appetizers, I'll draw 3 notes here. There's going to be 2 meals and 5 desserts. Okay, that was kind of badly drawn, so I'm going to draw those dots again. 2, 3, 4, 5. So the number of ways to choose a meal well, let's see. We could start here and go here and then, or we could start here and go here. We could start and go here and here, go here to here. There are all these different combinations. For each of these 3 dots, there's 2 dots that we can choose of meals. So there's a total of 3 times 2, or 6 lines here. But then accounting for the desserts, and I'm not going to draw in all the lines because it's going to get really messy on this diagram. Actually, I am going to draw all the lines in. But the way that it works, again, is that for each of these 6 ways, we again have 5 more ways. So in total, we have 3 times 2 times 5 ways, which is going to give us the total of 30 different meal options. And that's the multiplication principle. So the idea of the multiplication principle is that if some problem, and I'm just going to call them problems for now, can be broken down into some ordered steps. And ordered is really important here. The number of ways for the problem is the product of all the ways for the subproblems. One second, I'm going to move this device because my handwriting is really weird. Okay, number of ways for the problem is the product of the number of ways for the subproblems. And that's essentially it. Those are the 2 fundamental principles that we might want to go over. There are some other fundamental principles, but these are the 2 main ones. Okay, so now let's go over these definitions. Oops. Okay, so first of all, factorial. The idea behind factorial is that we're just multiplying the first n positive integers. So for example, 1 factorial is just 1, 2 factorial is just 2 times 1, which is 2, 3 factorial is 3 times 2 times 1, which is 6, 4 factorial is 4 times 3 times 2 times 1, and we can also remember that this is 4 times 3 factorial, and 3 factorial is 6, so 4 times 6, which is 24. 5 factorial is 5 times 24, which is 120, and so on. So that's the idea behind factorials. Now, an important thing to note is that 0 factorial is actually 1. And the reason that we make it 1 is that it works out nicely in math. So we specifically define 0 factorial to be 1 because it works out. Now, permutations are essentially arrangements of objects. So if we have a set of n objects, then any ordering of those objects is called a permutation of those objects. There are R factorial permutations of a set with n distinct objects. Actually, this should say n factorial permutations for a set with n distinct objects, and the number of ways to pick a k element permutation. So specifically, order matters here. So essentially, we're taking a list of k elements, and the order of the list does matter from this big set of n elements. And we can do this in npk, or n permutation k, ways, which is also equal to n times n minus 1 times n minus 2 times so on until n minus k plus 1. And we can also write this in terms of factorials by saying n factorial divided by n minus k factorial. And we also have combinations. Combinations are a way of choosing elements from a set. So here, order does not matter. We're just choosing. So the idea is that a combination is a way of choosing, and we are generally concerned with finding the number of combinations of size k from an original set of size n, and the number of ways to do this is NCR, or n choose R, or n combination R, and that notation, the parentheses with n and k, the parentheses with n and k, you would read that as n choose k, and it's equal to n factorial over k factorial times n minus k factorial. So those are the essential ideas for combinatorics. Now let's get in with the actual strategies. So the first strategy that we're going to talk about is casework. So casework is essentially a way that we use to break a big complicated problem into a bunch of small simple cases, and then we can just use the addition principle to add all the cases together to get our big problem. So let's start. So we're going to just work through examples and use those examples to see how casework works. So on the island of Mumble, the Mumblean alphabet has only 5 letters, and every word in the Mumblean language has no more than 3 letters in it. How many words are possible? So here we're just going to use the multiplication principle. So we want to choose words, but words choosing is, we do that with multiplication principle, but there's another problem in this problem. And that problem is that we don't know how many letters are in the word. Normally, if we were using multiplication principle, we would do it like this. We have maybe 3 letters, and then we would say, oh, there's 5 ways to do the first letter, 4 ways to do the second letter, 3 ways to do the third letter, and then multiply them all together with the multiplication principle, and get our final answer of 60, or whatever it is for that problem. But here, we don't know how many letters there are, so we can't just do something like that. But there is actually a way that we can do this problem. So the way that we're going to do is with casework. So we're going to use casework to get rid of that problem that we don't know how many letters are in the word. We're just going to do casework on the number of letters, because we know that in the language, no word has more than 3 letters in it. So the number of letters is going to be less than or equal to 3, and it must be greater than 0, because 0 letters does not count as a word. So let's do our casework. So we're going to say case 1 is when there are 1 letter, or is 1 letter. So this is a 1-letter word. In that case, we just have 1 letter. There's 5 letters in the alphabet, so there are 5 ways to choose the letter. So in this case, there's going to be 5 ways, and I'm going to circle that for our total for that case. Next, let's do case 2. So it's important to stay very organized when you're doing casework, which is why I chose to circle that 5. Here, again, let's use the multiplication principle. Here we have 2 letters, the first letter and the second letter, and then we have 5 ways to choose the first letter, and then for the second letter, we have 5 letters, because we can reuse the letters. So in total, there's going to be 5 times 5, which is 25 possible words. Oh, oops, not a box, because it's not our final answer. 25 is our total for this case. Now case 3. 3 letters. In this case, we again have 3 spaces. One of them is going to be, each of them is going to be 5 choices because we can have 5 choices for a letter in this language. And we have 125 possibilities. So for this case, we have 125. And have we counted everything? Let's see. We have 3 cases, one for 1 letter, one for 2 letter, and one for 3 letter. Now, we know that the language has only words that have between 1 and 3 letters. So this means that we have indeed accounted for everything. If we look at our sets using a Venn diagram style, like diagram, I guess. Not really a Venn diagram. Well, we have words, and then we have maybe 3 different categories. 1 letter, 2 letter, and 3 letter. There's 5 1 letter, 25 2 letter, and 125 3 letter. So in total, there's going to be 125 plus 25 plus 5, or 155 words in this language. So that's it. We've solved this problem, and we can go to the next one. Okay, so how many positive integers less than 10,000 have at most 2 different digits? Well, let's do this one. So again, if we have less than 10,000, this means that we can see immediately that the number of digits in the number is going to be between 1 and 4. So immediately you should be thinking, oh, I could do casework on the number of digits. Now, the other thing is, we have at most 2 different digits. So either there's one type of digit, or I shouldn't say type of digits. Instead, I'll say one unique digit, or 2 unique digits. Or maybe a better word would be distinct rather than unique. So here, how many positive integers? Well, let's try doing our casework on the number of digits. So let's start with 1-digit numbers. So I'm going to start with case 1. 1 digit. Well, in this case, we have 1-digit numbers. So how many positive? Well, all of them are going to have 1 unique digit. So again, we're going to be able to do 1 through 9. There's 9 possible ways for this case. Now what about case 2? 2 digits. Well, for every 2-digit number, we're going to have, we're going to have 2 distinct digits because it's only a 2-digit number. It can't have 3 distinct digits. So the total number of numbers here is going to be 99 minus 9, which is 90. Another way you could realize that there are 90 2-digit numbers is using the multiplication principle. There's 9 ways for the first digit because it can be 0 through 9. Or not 0 through 9, I mean 1 through 9. And there's 10 ways for the second digit because it can be 0 through 9. And multiplying these gives you 90. Okay, case 3. 3 digits. Oh, that's really bad handwriting. Okay. In this case, we have a bit of a more interesting problem. Well, we can do it 2 ways. We can break up into a bunch of smaller subcases, or we can try something that we're going to do later in the lesson, which is complementary counting. But since we're going to do it later in the lesson, we may as well do it now. So let's get a head start and look at complementary counting in this example. So in this example, or in this case, I mean, we have 3 digits, and we want at most 2 different digits. So what this means is that if we, well, let's take a look at this. So let's say this box has all 3-digit numbers. Now we're going to divide it into 2 parts. Numbers with 3 different digits and numbers with less than 3 different digits. This is what we want for this case. So what we're going to do is find the total number of 3-digit numbers, this big box, and then we're going to find the number of 3-digit numbers with 3 different digits, and then subtract this little box from the big box to get this side. So let's do it. How many 3-digit numbers are there? Using our multiplication principle, there's 9 ways for the first digit, not 0 through 9. It can be 1 through 9. There's 10 ways for the second digit because it can be 0 through 9. And there's 10 ways for the third digit because it can be 0 through 9. Now, the reason the first digit can't be 0 is because otherwise we get a 2-digit number or a 1-digit number. So in total we have 900 3-digit numbers. Now, what about 3-digit numbers with 3 different digits? Well, there's 9 ways to choose the first digit because it can be 1 through 9. Then there's 9 ways to choose the second digit because it can be 1 through 9 or 0 through 9, but not the first digit. So we get 10 minus 1 possibilities, which is 9. Now for this last one, we also have 0 through 9, but not first or second digit. So we have 8 ways to choose this last digit. So in total, we have 9 times 9 times 8, which is 648 different ways for this case, or 3 different digits. Now in total, this means 900 minus 648, which is, well, let's see, 252. Of those are going to be less than 3 different digits, which is what we wanted for this case. Okay, now let's finally deal with the last case. 4 digits. Okay, so now we want to have at most 2 different digits. So let's look at it. Now we're going to do our casework on 1 unique digit or 2 different unique digits. So I'm going to make a subcase 1. Sorry about the bad handwriting. 1 distinct digit. Okay, so we want to have 1 distinct digit in this number. So how are we going to do that? Well, if we have 1 distinct digit, it can be 1111, 2222, 3333, all the way to 9999. So there's 9 different ways. Now what about the next subcase? Here we have 2 distinct digits. Okay, in this case, if we have 2 distinct digits, there's a lot of different formats their number could have. Well, it can be, well, let's make the first digit A, because the first digit, well, let's just make it the A, and then let's make the other digit B. So our first digit is going to be A, so maybe we have A, B, A, B, A, B, A, B, B, A, B, B, A, B, B, A, B, 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 and that's it. So we have 7 different arrangements. And there's 9 ways to choose A, because it can be 1 through 9, because it's the first digit. And we have 10 ways to choose B, because it can be, actually, wait, no, we have 9 ways to choose B, because B has to be different than A, and it can be between 0 and 9. This gives us 81 different ways to choose our 2 digits. Oh, this gives us 81 ways to choose the 2 digits, but then there are also 7 different layouts that we can have. So 81, for each of those choices of 2 digits, there's 7 layouts. So using our multiplication principle, we get 567 different possibilities for this case. Okay, so that's essentially the bulk of everything. That's the computational part. Now we can just use our addition principle. So we've covered all our cases, so now all we have to do to get the whole problem is add everything together. 9 plus 90 plus 252 plus 9 plus 567. Well, if we group these 2 9s together to get 18, then add that 18 to the 252, we get 260, 270. Add that 90 to the 270. Well, then we got 360, and 360 plus 567 will give us that 927. Wait. Did I add that correctly? 9 plus 9, 18. 18 plus 282 would be 260, 270 plus 90, 360, and then 800, 127, so 927. Yep. So yeah, we have 927 different ways for this problem. And that's it. So essentially, casework made this problem really simple. And we got it. So let's go to the next example. Well, this example is a bit harder, so let's look at it. So each of 2 boxes contains both black marbles and white marbles. And the total number of marbles in the 2 boxes is 25. 1 marble is taken out of each box randomly. The probability that both marbles are black is 27 out of 50, and the probability that both marbles are white is m over n, where m and n are relatively prime positive integers. What is n plus n? This was from the 2000 AMEI. So let's get started. So here we're going to actually use some number theory and divisibility stuff. So let's do it. Well, we know, let's say that the number of marbles in the first box is A, and the number of marbles in the second box is B. We know that A plus B is 25. We also know that 50 divides AB, because 50 is in the denominator of this fraction. So 50 divides AB, but what does that mean? 5 divides 50, so 5 must divide AB. And recall from that number theory handout that we had, the modular arithmetic one, that this means that 5 must divide A or 5 must divide B. Okay, so what does this mean? If we look at our statement here, we have A plus B is equal to 25. But if we put this mod 5, let's say 5 divides A. Then if we look at this mod 5, we're going to have B is equal to 0 mod 5. And if we assume 5 divides B, then A is equal to 0 mod 5. So they both have to be divisible by 5. So that is important. So now, if both of them are divisible by 5, we only have a few possibilities for A and B. Specifically, A and B could be the pair 25, or not 25, 25. Or they could be the pair 15, 10. So now, if we have those 2 possibilities, we can break into casework. So case 1. 25. In this case, we have some number of black marbles divided by 20 times some number of black marbles divided by 5 is equal to 27 over 50. This means that B1 times B2 is equal to 54. Now, also, these are probabilities, so they must be less than 1. So B1 is less than 20, and B2 is less than 5, or less than or equal to. But this only makes one case possible, actually, where B1 is 18 and B2 is 3. In which case, we get 2 out of 20 white marbles times 2 out of 5 white marbles gives us a probability of 4 out of 100 or 1 out of 25 probability of choosing 2 white marbles. So here m plus n would be 1 plus 25 or 26. Now what about case 2? 15, 10. Well, in this case, we have b1 over 15 times b2 over 10 equals 27 over 50, which means that b1 times b2 is going to be 81. Now, again, we have b1 is less than or equal to 15, and b2 is less than or equal to 10. But what this means is that we only have one possibility again, because, well, we know that b1 and b2 are both powers of 3. So there's only one possibility, and that's they're both 9. And in that case, we get 6 out of 15 white marbles times 1 out of 10 white marbles is equal to 1 out of 25, a probability of choosing white marbles. And that gives, again, 26. So that's really interesting. Regardless of both of these possibilities, the probability of choosing both white marbles was always 1 over 25. That's pretty amazing. Let's go to constructive counting now. Okay, so constructive counting also is about reducing a big problem into smaller problems. But instead of breaking into different cases, we build from different cases to the big problem. So let's look at some examples, or one example. How many 4-digit numbers have exactly 1 0? Well, first of all, let's choose the 0, because, well, we're going to have 4 digits, first of all, so let's draw our digits out. Let's choose which digit is going to be the 0. There's 4 ways to choose which digit is 0, 1, 2, 3, or 4. And then that digit gets chosen to be 0, and we have 3 more digits to decide. Now the first digit, well, actually, that's wrong. The thing is, we can't have 4 different possibilities for which digit is 0, because the first digit cannot be 0, or else we don't have a 4-digit number. So there's only 3 possible digits that can be 0. Then we have the first digit and then 2 other digits. The first digit can only be 1 through 9. Oh, that's really badly written. So there are 9 ways to choose it. The other 2 digits can also only be 1 through 9 because we want to have exactly 1 0. So there's 9 ways. So 3, 9, 9, 9, using our multiplication principle, we can multiply everything together. 3 times 9 times 9 times 9 is 3 times 7, 29, which is 2,187. And that's our answer. So that was really quick and pretty simple. Okay, so let's go to complementary counting. So complementary counting, we already saw this. It's the idea of we have a big problem. So we divide it into 2 parts. The part we want and the part we don't want. I'm going to draw smiley face. So we take everything And then we take the part we don't want. So let's say this is everything. And then this is the part we don't want. And we do E everything minus the part we don't want is going to give us the part we want. So let's go to an example. How many 4-digit positive integers have at least one digit that is a 2 or a 3? Well, at least one digit, that is a big key giveaway that we're going to use complementary counting. Because if we look at our 4-digit positive integers, we can break them into two categories. At least 1, 2, or 3, or 0, 2s, or 3s. This is the part we want. This is the part we don't want. So let's start by finding everything. How many 4-digit positive integers are there? Well, we already learned how to do this. There's 9 ways to do the first digit because it can be 1 through 9. There's 10 ways to do the second digit because it can be 0 through 9, and so on for the other 2 digits. Multiplying those all together gives us 9,000 4-digit numbers. So that's our everything. Next, how many 4-digit numbers don't have any 2s or 3s? Well, that's easy too. Instead of having 1 through 9, we can only have 1 or 4 through 9. And how many numbers is that? That's 7. And then here we can have 0, 1, or 4 through 9, which is 8. And similarly for the other two, so multiplying everything together gives us 8 times 8 times 8, 512 times 7, which is going to be 3,584. Well, that's what we get, and then this is what we don't want. So now we take our everything, and then we subtract what we don't want, and we get what we want. So what do we want? Well, we have a 6, and then we have 1, 16, then 4, and a 6. So 6,416 different 4-digit positive integers that have at least one digit that is a 2 or a 3. And that basically solves that problem. So let's go on to the next. Actually, wait. This is not a 6. That is a 5. Oops, I can't subtract. So yeah, you should be very careful of not making those mistakes. 9 minus 3 is 6, but we have to carry a 1, so that's 9 minus 4. And obviously, rather than doing your subtraction like this, you might want to actually do the subtraction by hand on paper if you were in a competition to make sure that you actually get it right. Mental math is good, but having everything written out makes things easier to follow and check your work. So 6, 1, 4, 5. Okay, so now let's go on to this next example. A parking lot has 16 spaces in a row, and 12 cars arrive, each of which requires 1 parking space, and their drivers choose spaces at random from among the available spaces. Auntie M then arrives in her big fat SUV, which requires 2 adjacent spaces. So what is the probability that she is able to park? So this is actually a pretty difficult question. Well, it's not too difficult. We're going to be able to solve it, but it is pretty hard, and you need some insight. So this problem can be also solved with complementary counting. Excuse me. So, sorry about that, by the way. Essentially, the way that we're going to do this is by counting. Well, we're going to be working with probabilities here. So rather than counting ways, we're going to break into 2 different things again, but they're going to be probabilities again this time. Now, probabilities always add to 1, so our everything is going to be 1. Now, we want the probability that she's able to park. And the other one is the probability that she's not able. So this is what we don't want, and this is what we want. And everything is going to be 1. So let's try to get the part that we don't want, the probability that she isn't able to park. Well, in that case, we have 16 spots. Well, this is really bad trying. And 12 people come and park. Okay. So what does that mean? Well, there's 16 minus 12, which is 4 leftover spaces. And if Auntie M wants to park, 2 of those spaces are going to have to be next to each other. At least 2. Well, did you hear that key word, at least? Well, we're going to use complementary counting to count the opposite. So what is the probability that no 2 of those 4 spaces are next to each other? So that's our use of complementary counting. The at least isn't even explicitly in the problem. You have to think about it before you see that there is an at least in this problem. So the way that we're going to do this is we're going to see, well, we have 4 spaces, so let's figure out which of those 16, out of the 16, which 4 do we want? Well, we can't just choose any 4, because then 2 of them might be right next to each other. So we're going to use a really clever strategy. We're going to, rather than put those, select which ones or choose the parking spaces, we're almost going to insert them in and build our 16 set of parking lot. So let's start by putting in the 4 spaces. Now we want 3 spaces in between them. So as soon as we choose our 4 spaces, we're going to smush in 3 forced spaces. So in fact, after we choose 4 of our spaces, the rest 3 other spaces are going to be completely determined. They have to be parked in. So in reality, we're choosing those 4 from 16 minus 3 spaces because 3 of them are going to be predetermined right between those spaces, the 4 that we choose. So let's do 16 minus 3, choose 4. To get 13, choose 4, which is going to be 13 times 12 times 11 times 10 over 4 times 3 times 2 times 1. And this is just, I canceled out everything in my head, and you'll figure out how I did this soon. After you get a lot of practice, you'll realize how I did this. So 4 times 3, 12, and then let's cancel out more. So 13 times 11 is going to be 143, times 5 is going to be 915. So yeah, we have 915 different ways to choose that those 4 spots. And this is out of the total number of ways to park, which is, 16 choose 4. Actually, maybe I shouldn't have multiplied those out. I'm not going to multiply those out. Just forget that I ever multiplied them. It's 13 times 11 times 5. So we have 13 times 11 times 5 divided by 16 choose 4. That is our that is our probability. So 13 times 11 times 5 divided by 16 times 15 times 14 times 13 divided by 4 times 3 times 2 times 1. And let's do our cancellation. 1, 4, 3, 13 cancels. And we have 5 cancels. So in the end, we get 11 over 28. So 11 over 28 is the part that we don't want. So what is the part we want? 1 minus 11 over 28, which gives us 17 out of 28. So that is our answer, 17 over 28. And that's it. So that was a pretty difficult problem. The main thing was this 16 choose 3, or 16 minus 3 choose 4. The idea that we can squish in these parking spots between the 4 that we choose. And that turns out to be a pretty interesting and useful idea, not just in this problem, but it comes back in other problems as well. Okay, so let's go to pi. So pi is the principle of inclusion and exclusion, and it's a counting technique that computes the number of elements that satisfy at least one of several properties. So pi is actually very versatile, and it's really not very concise, but it is very organized, and you can use it to solve a lot of different types of problems. So pi might also look really complicated at first, but the thing is, you should never be afraid of using pi. Pi actually shows up a decent amount on like different competitions. And here we're only going to talk about 2 sets and 3 sets for pi, but you should never, and these are the simple cases where you can literally visualize it, but you should never be afraid of using pi on more sets than 2 or 3. In fact, on the AIOME in 2020, pi actually showed up. I think it was one of the mid questions, and it might have looked like pi would be overcomplicated with 5 sets for that problem, but in fact you had to use pi with 5 sets in order to solve the problem. So yeah. So let's go and do it. Also, because pi is so complicated and has so many calculations, some people call it a pi bash. What that means is that it's something that's really computational, and you have to do a lot of different arithmetic things. And that means that you have to stay organized and make sure you don't make computational mistakes, because those are really easy to make, and if you make even one, you're going to get the wrong answer. So let's start. So let's start with pi on 2 sets. So the easiest way to think of pi is with Venn diagrams. So let's look at a Venn diagram. So if we have 2 sets, A1 and A2, the number of elements in A1 here, we call that the magnitude of A1. And the number of elements in A2 over here, we call that, or I probably should have included more of the center circle. We call that the magnitude of A2. Now this part in between the two, this is called A1 intersect A2. So we say intersect to show that they intersect there. So that's the part that's in both sets. And the part that's in all of the sets is going to be A1 union A2. Excuse me. Okay, so what principle of inclusion and exclusion says is actually very simple. The magnitude of A1 union A2, so the number of elements in total in this Venn diagram, is equal to the magnitude of A1, so this blue part plus this green part minus this center part. So why are we subtracting the center part? Well, you might notice, if we have our Venn diagram again, I'm going to shade in where we're adding. So we just added A1. Now let's add A2. So now you can see, once we add those two, this center part gets counted twice. So we want to subtract one. So we subtract that by subtracting A1 intersection A2. So that's all the principle of inclusion exclusion says. It's quite simple, actually. So now let's look at 3 sets. Here, drawing a Venn diagram is not too difficult, but I'm not going to draw it. You can see through the equation. So the number of elements in this center part, A1 union A2 union A3, is the sum of the magnitudes of each of the individual sets minus the sum of the magnitudes of the sets intersected pairwise. So maybe AI intersect AJ plus the sum of the sets intersected 3-wise, or 3 times. So AI union or intersect AJ intersect AK. Okay, so that's basically it. So that's our principle of inclusion and exclusion. And if you look at the Venn diagram, if you can draw it out and see what this is. The idea is the same. We're starting with these sets, and every time we're subtracting out or adding back a part that was overlapped, so it got counted twice or completely erased. So that's the idea. Now let's try an example. This example is pretty simple because pi can get pretty complicated and complex to think about, but let's work through it. So suppose that there are 200 first-year students. So I'm going to draw my everything, or my universal set. That's what we call it in set theory. So 200 first-year students. So there's 100 are taking calculus, and 70 are taking algebra. So calculus, algebra. So there are 50 that are taking both. Now, how many are taking neither? Well, that's a good question, so let's see. So we know that 100 are taking calculus. So the magnitude of C is 100. And 70 are taking algebra, so the magnitude of A is 70. Now, we know that the magnitude of C intersect A is 50. So now we can use our principle of inclusion exclusion. The magnitude of C union A is equal to the magnitude of C plus the magnitude of A minus the magnitude of C intersect A, which is 100 plus 70 minus 50, which gives us 120. Now, what we want, if we interpret this with words, it's the students taking at least one course. So now we're actually secretly using our complementary counting. We know how many students are taking at least one course, so now how many are taking neither course? Well, we have our everything, 200, and we have our what we don't want, which is 120. Oops. So we subtract to get 80 students, which is what we want. This number of students taking neither course. So that is it for this lesson. We essentially covered all the material that we wanted. Yeah, that's basically it. So you can do the review problems. There are a bunch of different review problems and challenge problems, and that's it for today. So in the next lesson, both me and Mason will be there. So we'll see you there. Bye.